All right, good morning. Hope everybody's doing okay. Just want to say I apologize. I've got a slight cold, so if you hear me coughing or sneezing, just disregard that time of year. We're going to cover the heat of extraction rejection calculation today. Basically, it's the most important diagnostic tool that we have. So it's very important. I try to do this webinar once a month because it is that important. So my name is John Pendleton. I'm the Senior Trainer Technical Support at Enertech. There's my little mugshot there. If you need to get a hold of me, my direct line is that first number listed there, the 690-3275. If you need technical support, you can call the 664-5860, and that'll ring directly back to technical support to a group of us, so you'll get the first available person. But if you need any training information, manuals, anything like that, you can shoot me an email as well at john.pendleton@enertechgo.com. Today's webinar is recorded and it will be uploaded to YouTube later on today. So we have a YouTube site, which is Enertech University, and all of our webinars are, whenever I do a webinar, they're uploaded there. So you can watch this one again that you sit through today, or you can check out any of our past webinars as well. Obviously, there's no charge for those, so definitely check out those videos. It's a pretty good resource for us. We also have Enertech University website. So if you go to that, you can go to enertechusa.com, and there's a link to Enertech University. Or you can just go to Enertech University and you can see any upcoming trainings that we're going to have. I try to have webinars once a week on Wednesdays, sometimes more, sometimes less, depending on what time of year it is. But hopefully we'll be back to in-person training soon. Just kind of waiting all this COVID stuff to clear up. So definitely check out our website and any upcoming trainings there. So with heat of extraction or heat of rejection, extraction is when we're in heating mode, rejection is when we're in cooling mode. The way we do the calculation won't change from heating or cooling. It's just what we're doing, whether we're pulling heat out of the ground and putting it into the home, which would be heat of extraction, or whether we're picking up heat from the home and putting it into the loop field. That would be the heat of rejection. But with that, there's no need to pull out your refrigerant gauges and throw them on the system right away because it verifies performance of the unit by measuring the heat that's being extracted or rejected to or from the loop field. So basically, with heat of extraction or rejection, you're going to need a water pressure gauge with a needle. We'd recommend a digital pressure gauge. Sometimes we deal with some pretty small pressure drops, like 1.2 psi. So it's kind of hard to see on an analog dial gauge. So I would recommend a digital gauge, and we do have one available. It's a Dwyer gauge. It's what I use, and we do sell that at Enertech. You'll have to get the needle separate that'll thread onto it, and we have those available as well. And then we have a digital thermometer, and I think I may have a picture of it coming up, but it's made by Cooper, and it's got a tapered end on it, so it goes into those pressure temperature ports pretty easily. So we do carry both of those. You can get them online, I'm sure, as well, but you're definitely going to need a digital thermometer and a pressure gauge, and you're going to need the IOM or the contact number for tech support, where we can look it up in the IOM, your heat of extraction and your pressure drop. Because we're going to compare the numbers that we calculate with what's in the catalog, in the IOM. When we do this heat of extraction or rejection, it's very important, especially on new installs, that we're installing pressure temperature ports. If we don't install those, it's hard for us to establish water flow. We can get some temperature differences on a pipe, on the outside of a pipe. It may not be the true temperature of the fluid that's inside that pipe, but it's going to be not too far off, and your temperature difference across two pipes will probably be the same. So it's not as important on temperature, but if we've got to know what our flow is, we've got to have those pressure temperature ports installed. With a non-pressurized system, we can figure out flow with a flow meter. With a pressurized system, it's sealed. So the only way to know is by using the IOM and looking at pressure drop. So make sure your installers are always installing pressure temperature ports. If you've got a water-to-water unit, make sure they're on the load and the source water lines, because we're gonna have to check water flow on the load as well. So when in doubt, put a pressure temperature port in. They're pretty cheap. It's a lot cheaper to put them in on install than it is after the fact. So we're always gonna check the unit when running in second stage, if it's a two-stage unit. And we're going to normally turn the desuperheater off. There's a couple ways of doing that. The newer unit will have a switch on the side of the control box. The older units, you'll have to go to the Molex plug that goes down to the pump and just unplug it, so the pump's not running. Normally, the desuperheater is going to pull somewhere between 3,000 and 5,000 BTUs from your heat of extraction. So it may be a little bit off from what's in the manual if the desuperheater is running. We do have heat of extraction and rejection worksheets in the back of the IOMs. So if you can fill out that information, if you're not sure how to really do it, you can get as much information. You can call us in tech support. We do the calculation numerous times a day, so we can get it for you real quick and look and see how you're doing on performance. So the first thing we've got to really understand is the engineering data, or the IOM. So we'll cover that real quick. This is an example of an extended data chart in the IOM, the spec catalog, whatever you want to call it. But this is an 036, so it's a 3-ton unit, forced air. I'm not really sure, it's by an XTE or something like that. But so you'll see we've got EWT. That stands for entering water temperature. That's the source entering water temperature. So normally in our manuals, we're pretty good, especially now going forward. In this chart, we see a 30, a 50, probably be a 70 and a 90. And that's kind of a big temperature difference. So if you had 40-degree water, you'd have to kind of interpolate this chart. So we have broken it down. I think now we have 25-degree, 30-degree, and then we go to 10-degree increments. So 40, 50, 60. So we can get a little bit closer to where you're at. We do have a correction chart, factor chart in the IOM as well, if you're outside of ranges of these water temperatures or air temperatures. To be honest, I don't use that chart very often unless the number is outside of range, then I might look at that chart. But I've only used that correction factor chart maybe a handful of times in my 8 years here at Enertech. So again, entering water temperature is just that. If you look at our heat exchanger, you're going to see that we have a source in and a source out. And so we're going to check the temperature at their entering water temperature. So your source in your source inlet connection. The next is your flow rate in GPM. And you'll say, well, what am I? This one is 5, 7, and 9. You'll say, well, we'll just pick the middle one. Well, that's not how we really do it. You have to do pressure drop in order to know what flow it is, and you've got to have the IOM in order to know what that pressure drop converts to GPM. We don't have a calculation or a formula that I can give you that says if the water temperature is this and the pressure drop is that, your GPM is this. That's in all these GPMs, and your pressure drop are all figured out in engineering in the lab. And so we've got to have the IOM in order to know what the GPM is. So basically what we're trying to figure out is in that heat exchanger, how much water is flowing through the heat exchanger in 1 minute. Too much, and we're going to have, or the performance is going to be, the efficiency is going to be low. If we don't have enough water flow, we're not going to, our heat of extraction or rejection is going to be low, and we're going to be probably tripping out on a low or high pressure. So we've got to make sure we have enough water flow per minute through the heat exchanger. And we do that by checking the pressure drop. So that's where our pressure gauge comes into play here. I told you we needed a digital pressure gauge. Basically what we're going to do is we're going to check the pressure in and the pressure out. And we're going to just do the math on it. So if we had, you should always have higher pressure in than you do leaving, because we have pressure drop throughout that heat exchanger. If for some reason you have higher pressure in, or excuse me, lower pressure in than you do out, then your flow is reversed. The unit will probably underperform a little bit. It'll still work. It just won't transfer heat quite as well due to the rifling that's in the heat exchanger itself. So when we look at GPM, we've got to get our pressure drop. So pressure in minus our pressure out. That'll give us our pressure drop. So if we had 3.4 pounds of pressure drop, that would equal the 7 GPM at 30-degree entering water temperature. The feet ahead we don't really use. The feet ahead is used if you need to size the pump. That's how much pressure drop in feet ahead that heat exchanger has. So if you need to size a variable speed pump or a fixed speed pump for the unit in your loop field, that's one of the numbers we would use. EAT, that's the entering air temperature on your return air. So sometimes, normally I think it's 80-degree return in heat and cooling and 68-degree in heating. So if you have 65-degree air, again, here is that another correction chart, another one that I haven't used very often. But if you're outside of your return ranges, you can use this correction factor. Again, I don't use it very often, and I doubt that really you will as well. So. The next is our heating capacity. So heating capacity is basically we have what's called heat of compression and heat of extraction. Your heat of compression happens in the refrigerant process. The compressor produces heat. And in heating mode, well, we've got to do something with that heat. We can't just leave it there. So we pick it up in the refrigerant circuit and we'll put it into the home with what we're pulling from the ground. So if you look at this chart, you'll see heating capacity, and right next to it in that yellow box is heat of extraction. Heat of extraction is what we're pulling from the loop field. Heat of capacity is what we're putting into the home. So heating capacity will always be higher than your heat of extraction because it's what we're pulling from the loop field plus what we're getting from the heat of compression. And we add that to the heat of extraction, and that gives our total heating capacity. We can actually figure out what the compressor is producing as far as heat. There's a formula. If you take volts times amps, that equals watts. So on a compressor, we can go to the contactor and we can check what our voltage is, probably 240, 230, somewhere around there. And then we can take an amp draw on the compressor. So let's say the compressor amp draw is 20 amps. We would take that 20 amps and divide and multiply that by our volts. So 220 times our amps equals watts. Now, watts don't really mean a whole lot to us. So, whatever watts we get, if we multiply that times 3.41, that gives us BTUs. So we can actually figure out what we're producing with the heat of compression what the heat of extraction is. With that heat of compression, we can figure out how efficient the unit is running. It's a good calculation when we get into a homeowner says they have high utility bills. We can take a look and kind of see what the actual unit is doing. Is it overamping? Is our heat of extraction low? And it'll give us a COP number that we can compare to here what's listed here in this manual here. So again, here's a little picture of the heating capacity. So if we've got 30,000 BTUs we're pulling from the loop field, we've got another 10,000 BTUs for heat of compression. So total heating capacity of this unit would be 40,000 in this example. We can actually take that 40,000, divide it by our supplied power, or our 10,000 BTUs, and that's how we get our COP. So heating capacity divided by our energy delivered. And in this example, 40,000 divided by 10,000 BTUs would be a 4.0 COP. Usually it doesn't work out quite that nice, but that's basically heating capacity. Your heating capacity will always be higher than your heat of extraction, and your heat of extraction will always be higher than your heat of rejection will always be higher than your heat of extraction. In cooling mode, we pick up the 40,000 or the 30,000 BTUs from the home. We pick up the heat of compression as well. We have to do something with it, and we send all those BTUs to the loop field. So we'd put 40,000 BTUs in the loop field in cooling, but we're only pulling 30,000 out in heating. So heat of rejection will always be higher due to the heat of compression. It's almost like free heat, the heat of compression, when we take that heat. I do cover that a little bit further, maybe even in this section, but definitely in some geothermal diagnostics and troubleshooting. So I may even have that one going on later on this month, so you might want to check that out. The next column is HE. That stands for heat of extraction, and that's what we're pulling out of the loop field there, that 30,000 BTUs. And that's what we're basically going to cover today. We'll cover a few examples on that, so you guys can feel pretty comfortable about doing that, or at least getting the information and giving that to tech support so we can figure it out for you. Leaving air temperature, that's your supply air temperature on the unit. So normally we have about a 25-degree temperature difference, depending on airflow, obviously, but that's leaving the unit. So if you have 65 coming in, you should probably have roughly about 90-degree supply air temperature. The next is your input and power. That's in kilowatts. And basically that's the volts times amps equals watts. That's a pretty simple calculation. I do it quite a bit, so I remember it quite a lot. But I do keep an equation chart kind of on my desk of different formulas and things. And if that's something you'd like me to send over to you, I definitely will. Just shoot me an email or give me a call with your email address, and I'll send over that formula chart and anything that you need from this training today. COP is how efficient the unit is, coefficient of performance. And that's basically energy delivered divided by energy supplied. So we're delivering 40,000 BTUs, and we're supplying it with the compressor and the voltage, which is, in this example, the 10,000 BTUs. Volts times amps equals watts. So energy supplied, or energy delivered, divided by energy supplied. And that gives us our COP. And this would be a 4.0. So here in this example, we had 2.47 kilowatts and 30,000 BTUs supplied to the home, 21,000 BTUs supplied from the ground loop. So roughly 9,000 or so, 8,300 BTUs of heat of compression. So if we took that 8,300 and divided that into the 30,000, that would give us our 3.58 coefficient of performance. In cooling mode, sorry, got a little button happy there. In cooling mode, we use heat of rejection. And you'll see that heat of rejection and total cooling. So total cooling is what we're pulling from the heat that we're pulling from the home, the amount of BTUs we're pulling from the home. In heating mode, we don't, I know like if you go to a register, you feel cool air coming out. We don't cool the air off. We actually pull heat from the air, which in turn cools it down. So the total cooling, that's sensible and latent, that's what we're pulling from the home. That's what we're removing from the home. So you'll see that heat of rejection is higher than your total cooling capacity. And that's due, again, to that heat of compression. We pick up that heat of compression and we'll reject that into the loop field as well. So that's why it'll always be higher than your total cooling capacity or your heat of extraction because of that heat of compression. So how do we perform the calculations and the measurements? So before a system can be properly diagnosed or serviced, we must establish that we have airflow and we have water flow. Now, when we do pressure drop, that's going to tell us water flow. Got to have pressure drop. You don't have pressure drop, you don't have water flow. Airflow is pretty simple. We have an ECM board in our forced air units, and you can count the blinks and it'll tell you the CFM. If you got an older unit and it doesn't have a CFM light, for one, you can usually hear the fan running and you can feel airflow coming out of the registers. So you kind of know you've got airflow. With water flow, you shouldn't be able to hear it. If you can hear it, you've got air in the system and you really can't really feel it. So that's why we got to get pressure drop. But make sure we've got airflow and that we've got power, that the unit is running, that the compressor is operational. And then we can check our water flow. We can check with pressure drop, and that'll start our heat of extraction, heat of rejection calculation. So here on the left is a digital pressure gauge. This is the one that we offer. It's a Dwyer gauge, 0 to 100 PSI. The black and red digital thermometer there, we used to hand these out in trainings, but it had a really wide shaft on it, and it gets stuck in those PT ports. You got to pull it out, and the head and the wires will come out of the thermometer and leave the shaft stuck in there. So I recommend the one on the bottom. It's a Cooper. I think I've got mine on Amazon, but again, we do offer these now. And you can see the tip of that thing is kind of tapered, so it really goes into those PT ports quite nicely. Those are really the only tools besides the IOM that you're going to need. The only other thing are these pressure temperature ports where we've got these arrows pointing to them. And you can have them at the unit, like shown in this picture, or sometimes they do put them right near the flow center, which is fine with me. Basically, it's a brass fitting with a neoprene gasket in the middle with an X cut in it. And so you just insert it into the gasket there. Over time, these will leak a little bit and may spray a little bit of water as you pull your needle out. They do have a cap on there that'll seal it off. So don't really worry about that too much. If they are, dribbling a little bit of water, just happens over time. On a non-pressurized system, in order to verify water flow, we need to use a flow meter tool. Now you can put a flow meter tool in the water circuit and leave it. Over time, you're not going to be able to read it though, so I wouldn't really recommend it. This one is more of a portable. It can just be put in for a few minutes and taken right back out. There's a dip tube on these non-pressurized flow centers with a cap on the top. You take the cap off and hook it onto that dip tube and then dump back into the flow center. Don't dump back like it's showing here in this with that open end. And then the flow meter will float and tell you how much water flow you have. Now on the newer non-pressurized flow centers, the NP, the composite cabinet, the black NP variable speed flow centers, and the black composite fixed speed flow centers from the non-pressurized, we now can use a pressure gauge to check pressure drop and water flow. The older QT style, the white cabinet, that you'll have to have a flow meter tool for, because the pressure drop isn't accurate. It won't give you proper water flow. Just a slight note there. So here is the magical heat of extraction rejection formula. So it's Q, which is BTUs. That is figured out by TD, which is temperature difference between your entering and leaving water, times your GPM, which is your pressure difference converted to GPM, and your brine factor. Now, I'm going to tell you brine factors multiplied are found by multiplying the weight of the fluid times 60 minutes in an hour. Yeah, okay, sure. I'll remember that. Really, all you got to really know is we use 500 for pure water and 485 for any time we have a water or antifreeze mixture. The 485, we normally will use propylene glycol, ethanol, or methanol. And they kind of range a little bit. I think propylene glycol might actually have a brine factor of 491, and maybe methanol has a 483 or something like that. But this is an average, and it'll get you where we need to be. So 500 for any time we have pure water, which would be like an open loop system, or if you're down in the Caribbean or southern Florida, where we don't have to worry about the water freezing. And then use 485 for any time we're using antifreeze in our loop field. So closed system where we're going to get below freezing on our water temperatures. This is actually the antifreeze capacity chart here, and you can look at the capacity factor. Actually, I was wrong. Propylene glycol at 30% is 483. Methanol at 20% is 490. And ethanol is a little bit higher, but again, it's just an average. So we're 485 for antifreeze, 500 for water. That's really all you got to know. You'll also, when we look at our IOM, we do have like a 30 degree, 40 degree, 50 degree. We have, again, we have those 3 flow rates listed. Now, we don't want you to, say, well, I do have 2.1 pound pressure drop at 30 degrees, so that's 6 GPM. Well, that's fine for an open loop. These flow rates, the first flow rate is the minimum flow rate for an open loop. On an open loop, we consider that like a pump and dump. We're pumping from a well and we're dumping back into a drain, or we're pulling out of a lake and we're dumping back into a pond. Something where we're not reusing the water. We don't want to waste a lot of water, and that water is normally at a very consistent 50 degree temperature. Now, that's got to be a well. A lake could drop temperature lower, so you probably want a little bit more water flow so we don't freeze our heat exchanger. But on an open loop, the well water is always right around 50 degrees. So we don't have to worry about it freezing, and it's very consistent, and we can use less water flow. So the minimum flow rate for an open loop system is 1.5 GPM per ton. Now this is a 4-ton unit, so 1.5 times 4 is 6 GPM. Our next flow rate is the minimum flow rate for a closed loop system. The minimum flow rate for a closed loop is 2.25 GPM per ton. So this would be 9 GPM on a 4-ton system. 4 times 2.25 is 9. The final flow rate listed is the recommended flow rate for a closed loop, which is 3 GPM per ton. That's what we're trying to move through the system. So 3 times 4 is 12. So the first flow rate is open loop. Second flow rate is minimum flow rate for a closed loop. And the third is the recommended closed loop flow rate. So 1.5, 2.25, and 3 GPM. So we'll do a little flow rate example here. We've got a YTO48. We've got 30-degree entering water temperature, 40.8 PSI in, and 36 out. So if we do the math on that, 40.8 minus 36 is 4.8. Now that's not flow, that's PSI drop. So if we go back here and look at this chart, we go to the 30-degree entering water temperature. We had a 4.8 pound pressure drop. So it tells us that that's 12 GPM. So now we know that we've got the recommended flow rate for a closed loop system. Again, if your PSI in is less than your PSI out, then your flow is going backwards through the heat pump. I have seen it occasionally from the factory where someone at the factory put the stickers on backwards. We've got a process now to eliminate that, but it has happened. So if you know, again, if you see that PSI in is less than out, then we know our flow is reversed, or your flow center is going the wrong way or something like that. So again, pressure difference in minus the PSI out. That's going to give you our pressure drop. Again, that's not GPM, that's just pressure drop. So here we've got 40 in, 36.6 out. This will give us a 3.4 pound pressure drop. So here, if we look at this chart, I'm going to tell you we had 30-degree entering water, 3.4 pound pressure drop is equal to 7 GPM. So this is the minimum flow rate on a closed loop system. That's what this flow rate would represent. There's possible maybe you could have a variable speed or a 2-pump flow center and you're staging those pumps and it's in second stage, but normally that's a minimum flow rate for a closed loop system there. Temperature difference, if you can do math, you can do temperature difference. So if we have the entering water temperature here of 36.8 and we're leaving at 31.2, we just really do the math and that gives us our temperature difference on it, 5.6. Normally we're going to be somewhere between 6 and 8 degrees depending on water flow for a closed loop. And an open loop we're going to normally have about double that, so 12 to 16 degrees. In a closed loop, we're moving half the water flow that we are in an open loop. In a closed loop, we're moving double the amount of water flow that we're moving in an open loop. So the longer the water is in contact with the pipe, the more heat transfer that takes place. So if we move the water at 1.5 GPM per ton compared to 3 GPM per ton, we're going to get about twice the amount of temperature difference. So if this was an open loop, we may see, a 12-degree temperature difference instead of this 5.6. So here is our example, heat of extraction, heat of rejection example. So this is a packaged unit. We're on second stage, which is high speed on a closed loop. So if we had entering water temperature of 52 roughly and leaving at 44.9, first of all, let's look at this first. It's entering at 52, leaving at 44. So our water temperature is higher than what it's leaving at. So we're extracting heat from that water. So we're in heating mode. So the temperature difference would be 7.2. Now, pressure difference, 52.4 minus 47.6 is 4.8 pound pressure drop. Now I'm going to tell you at 50 degree entering water that at 4.8 pressure drop, it's going to be 12 GPM. So now, as long as we know our GPM, we know our temperature difference, we know whether it's got antifreeze in the system or not, now we can just do the calculation. So we take that temperature difference times our GPM times our brine factor. That's going to give us a number, 41,904 BTUs. So if we look on the performance table of the XT unit at 50 degree entering water, it's showing us that we should have a capacity of 40,100 BTUs. So as long as we're within 10% of what the manual says that we should be, then the unit's operating fine. Normally, we won't be higher than the unit. Sometimes, occasionally, we will. Maybe we're not really moving 12 GPM. Maybe we're really moving 11 GPM. But we're within 10%, so there's really no reason to really worry about doing anything else. As long as it's 10% above or below this IOM number, then we're good to go. There's no need to put refrigerant gauges on and try to diagnose the system. The system is doing all that it can. So we'll go through a couple practice exercises here real quick. And a lot of times I know we're going to give you CFM levels and it lists those in the IOMs. It doesn't really change the BTUs that much. So if you don't know what your CFMs are, don't really worry about it too much. It may affect your BTU output by 1,000 or so, but don't really worry about it too much unless we're outside of that 10%. And then we may look at your, that'll make us look at other things. So we may look at the airflow at that point. So here we've got a YT unit, which is a packaged unit. We do have methanol in the system, so we do have antifreeze in the system. We've got entering water pressure of 49 and leaving at 46. So if you do the math on that, we have a 3 PSI pressure drop. You can see that's not a lot of change or difference in the two. So that's why that digital pressure gauge is really going to help out. We have entering water temperatures of 53.5 and 44.6. So if we do the math on that, it's roughly 8.9. So now we know our temperature difference and we know our pressure drop. Once we know our temperature difference, we can look up in the IOM. We know that our entering water temperature is higher than our leaving water temperature. So that tells us we're in heating mode. The brine factor for methanol is 485, and we've got a 3 pound pressure drop. So if we know our entering water temperature is 50, we go to the IOM, we go to a 50 degree mark, and we had roughly 3 pound pressure drop. So that tells us we have 9 GPM. So we need to remember that number. So now we know our GPM, we know our delta T. Now we can do the math. So we run the formula, 9 GPM times our temperature difference times our brine factor of 485. Now give us 38,848 BTUs. Now, you can say, well, that sounds good, but we need to go ahead and compare that to the IOM that we just had pulled up. So we'll go back here to that 50 degree entering water. We had our 9 GPM, and we had 1,600 CFM. So we want to follow that column down where the HE is located. And we'll see that we should have 39,600 BTUs. That 39.6 is equal to 39,600 BTUs. So we measured 38,800. The catalog says we should be at 39.6. So as long as we're within 10% of the 39.6, which would be roughly 35,600 BTUs on the low end, then we're operating properly. So we're within 10%, the unit is operating properly. So yes, the unit's operating properly. No, we don't need to put refrigerant gauges on there. One of the reasons we want to do this calculation first before we just go throwing refrigerant gauges on there is the system is sealed. And every time we put gauges on there, you're going to pull a little bit of refrigerant out. Over time, you're going to get low on refrigerant. And so that's why that's one of the good reasons to go ahead and do the heat of extraction or rejection before we ever decide to put refrigerant gauges on there. When you're out there doing maintenance, your annual maintenance, you can just leave your gauges on the truck. If there's a problem, then you can go ahead and get them. But and always do the calculation when you are doing your annual maintenance. That way you can make sure it's not slowly dropping, water pressure, and you've got, your proper water flows and things like that. So we'll go ahead and move on to another exercise here. This one is a XT060, so again, another packaged unit, and we're going to be at 1950 CFM, and we're in second stage on the compressor. So first, we're going to check our pressure drop. So we have 23.5 in and 21 out, so 2.5 pound pressure drop. Next, we'll look at our temperatures. We had 48.7 degrees in and 67.9 out. As you start to work with Geo more and more, you'll kind of notice temperature differences quite a bit. And so you'll see this one and go, wow, I have a 20-degree temperature difference almost. I guess you can probably figure that either you don't have enough water flow or it's an open loop system. Now, you may be able to tell it's an open loop system, but temperature differences will also let you know how the system's running before you even do heat of extraction. If you know you've got proper water flow and you have 1 degree temperature difference across that heat exchanger, then we probably know something's going on. In this example, if you have a flow center, with pumps, you may see this and go, well, I may not be moving enough, so we need to check that pressure drop. Because normally, again, going to be about 8 degrees on a closed loop, about 16 degrees on an open loop, depending on flow rates. So you'll look at this and kind of see. Now, again, we're coming in at 48.7 and we're leaving at 67.9. So our temperature of our water entering is lower than what we're leaving. So we're actually picking up heat from the home and putting it back out into the loop field or getting rid of it. So we're in cooling mode in this example. So we're in cooling mode. The brine factor for straight water, so H2O, is 500. We had a pressure drop of 2.5. Excuse me. So now we can look in the IOM. Excuse me. We had roughly 50-degree entering water temperature. We had a 2.5 pound pressure drop. I've got the feet circled there. Sorry about that. I think I switched this over from a square screen to a wide screen, and it kind of threw a couple things off. But we're at 2.5 PSI pressure drop. So that's going to equal 7.5 GPM. That 7.5 GPM is the recommended flow rate on an open loop system. So that's that 1.5 GPM per ton, which is why we have that wide temperature difference of 19.2. So now we've got all the numbers, we can just do the math on it. We run the formula, 7.5 GPM times 19.2 temperature difference times our brine factor for straight water of 500. We do the math on that, that's 72,000 BTUs. So it doesn't sound too bad, but we'll go ahead and we'll look it up in the spec manual here. So again, we had 50 degree entering water, 7.5 GPM, and 1950 CFM. So now we're on the heat of rejection. Don't go to the heating side of the chart, go to the cooling side, and we'll check HR. So we'll follow that down to the 1950 CFM. Actually, it's above, up one chart, the 80,400 BTUs. So we measured 72. The catalog specifies it's 80,400 BTUs. So is the unit operating properly? Yeah, it is operating. It is within 10%, but it's real close. It's only about maybe 40 or so BTUs above that 10%. So on this example, there's a couple ways to look at it. I'd probably look at why I was called to the home. Was I called there because the unit's not keeping up? Was I called to the home just for preventative maintenance? If you're called there because it won't keep up, you may want to dig into it a little bit deeper. It could just be maybe the air filter is dirty and we're not transferring all the heat we could in the air coil. You know, if it's keeping up and you're only there for maintenance, I would probably make a note on the ticket of what the BTUs were and to make sure that you check it again the following year to make sure that number hasn't gotten even farther outside of its range. But it is operating within 10%, so there really is no need to, you know, put refrigerant gauges on there unless for some reason they called because it's not keeping up. And then they probably just sized the unit too tight and it's really cold outside or something like that. But again, yes, it is within the 10% in this example, just barely, but it is within specs. We'll go through, I think we've got one or two more of these here real quick. This is a packaged unit, 036, 1240 CFM, and we've got glycol in the system. We'll start with pressure drop, and it doesn't matter if you check temperature or pressure drop first to me. It's not really that big of a deal. So here we have a 3-pound pressure drop. We'll check their temperature difference. We have a 3.2 degree temperature difference, which seems kind of low. But we'll just look in the manual and see what we've got. Now, the water temperature in is higher than it's leaving, so we're in heating mode. We're extracting heat from the water itself. Brine factor for glycol is 485. We had a 3-pound pressure drop. So if we look in the manual, we'll go to our 30 degree, 3.3, roughly 3-pound pressure drop. That equals our 9 GPM. So now we know our GPM, our temperature difference is 3.2. So if we do the math on that, we take our 9 GPM times our temperature difference times our brine factor of 485. That gives us 13,968 BTUs. So 3-ton unit seems kind of low. We'll look it up in this spec manual. Again, we're at 30 degree, 9 GPM, 1240 CFM. On the heat of extraction, we should be at 22,700 BTUs. So we know we are at 13,000. The catalog specs 22,700. So are we within 10% of that? Negative. No, we are not. We're about 67% capacity on this. So we would have to dig in a little bit deeper on this. In this example, I wouldn't immediately go throw my refrigerant gauges on there. This YT unit is a 2-stage unit. And in first stage, we run 67% capacity or 2/3 capacity. So the first thing I would check on this, make sure that the thermostat is calling for your second stage. If so, then check your solenoid on the compressor itself and make sure that it's staging up, that we're getting that extra 1/3 capacity. If you want to know how to check, make sure that the compressor is upstaging the second stage, amp draw is the best way to know. You can put an amp clamp on there, and the compressor amp draw should go up 3 to 5 amps. So that's going to let you know whether it's in first or second stage. Sometimes you can hear it shift, sometimes you can't. But in this example, it's not operating properly. And just from observation with the 2/3 capacity, that's the first thing I would check on this. So on this example, we would definitely have to dig in a little bit deeper. We do have just a heat of extraction rejection video one of our older trainers did back in the day, and it should be located on YouTube as well. But you can check out today's webinar, or you can go and check out the heat of extraction rejection video as well. So that's really all I have for today. If you have any questions or comments, you can ask here. I'll wait around for a few minutes. If not, you think of something later on, definitely reach out, either technical services, or you can reach out to me, or you can reach out to the training email as well. The training email is basically just training@enertechgo.com. So I have lots of email accounts, so I can get you can get a hold of me one way or another. But again, thanks for joining today, and have a great week.